Yay. Hello, everybody. Um, Welcome back. Day 2 of binary exploitation. Nathan's going to be talking about some
Binary exploitation.
pretty, yeah, binary exploitation, but some pretty tough stuff. So, if you were not here for Mondays, and also probably you want to have watched the reverse engineering before you come to this, so you can stick around and you'll get something out of it. But if you want to really understand what's going on, I would advise going back and watching the reverse engineering and then the day 1 of this week on from Monday. Um, and
Yeah,
yeah, so
sweet.
go ahead, take it
Binary
away.
exploitation
Talk
day two.
about part 2.
So, as Rowan said, RE1 day one, Pwn1 day one. Those are the big prerequisites for this. Um, I'll watch the chat as per usual. Say hi. You follow along the
Thank you.
Docker container. I got mine running right here. I have already cloned the repo this time, unlike last time, which is nice. You should be able to clone it from
Nice.
that same link. Yep. So just a refresher of what tools we're using. GDB with Jeff. I tend to pronounce this GEF, it's actually Jeff. Python 3 with Pwn tools, we'll be still using a ton of that today for each of the demos. I'll be writing a solve script for you. And one gadget, which we'll be using somewhat today. It's not installed on the Docker, but I'll demonstrate on my system just so you can see how that works. Checksec, Rob gadget, a few others. A lot of times just being Pwn tools and tools that come with it. And then Ghidra and RE tools, which we won't be using today since we'll have source code, but we'll be using them a lot for Pwn challenges. So just a refresher of what we did on Monday, I guess. So first demo we had was Introduction to Pwn tools. Saw some solve scripts for that. Let's see if I can. Example 1, solve. We just read input, we're able to parse it to get our leak out of it, and could send it with the value to overflow with a simple buffer overflow of a variable. You can see that we've had to first deal with iterator I, and then we could write the value that we wanted to the least significant byte of the return address to jump to a and then we talked some about leaking libc and the global offset table, which we'll review a little bit today. Today, the plan will be to first, we're going to review defenses just as a refresher and to go in a little bit more detail about a couple of them. Then we're going to talk about stack canaries and ret to libc. And then we're going to have an example with some format strings using printf to exploit binaries. And then we're going to talk a little bit about heap exploitation, which is a massive topic in itself. We could spend a whole week talking about it, but we'll do a little bit. So first, just defenses. ASLR, we talked about ASLR pi NX to some extent yesterday. ASLR will randomize your stack locations as well as locations of loaded libraries. So every time you run the program, these addresses will be different, but the address of your program itself, example 1 in this case, this will be at OX 400,000 single time. And pi, position independent execution. This will randomly choose which address the program is loaded into memory at. So here you can see that this address totally different from 400,000, and every time you run it, it will be different. Example 3 in our case was running with pi. What's Rowan up to? It's exciting. But there's non-executable memory here, and you can see that it's marked as executable and writable if NX is disabled. If non-executable memory is enabled, then you could see it's like previous examples that we looked at their memory. So what NX does is it ensures that writable memory is never executable. And this protects against shellcoding attacks or attacks where you can jump to memory that you can write to as well. And so stuff like the stack and heap will not be executable. And then railroad. So I briefly mentioned it just in an answer to a question on Monday, but I'll go in a little bit more detail about what exactly railroad is. Railroad stands for relocation read-only. Rowan talked about how relocation happens in detail during the RE presentation. But the idea is that when you call a function, it'll look up in the PLT where printf is or whatever function you're calling. And it calls the code in PLT, which will look up the got entry. And if it's the first time you're running it, it'll actually jump to this fixup function, which will find the address of printf and load it into the got instead of where the fixup entry was. And then it will jump back to the top of the PLT entry. It will call got entry, which is now, when it looks it up, it's a pointer to printf itself, and then it can execute the code in libc. Relro protects against got exploits, which we did one of yesterday, or Monday, where we could overwrite the got entry. So when we were able to control this address, we can make it something other than printf, like system, for example, and execute code of our desire. But Railroad fixes this by marking the got as read-only. So what that means is you call printf, and it looks it up in the got, and it's already there in the got. It's loaded at the very beginning of when the program's loaded in the memory, and then the got is marked as non-writable. So it's able to look it up, and it will execute the actual printf code without worrying about overwriting a got entry. And then the last major protection that we're going to talk about is stack canaries. Sometimes you can also hear them called stack cookies. And the way that they work is a random value is inserted on the stack just before the save base pointer and instruction pointer. And then it will be checked as code is executed right before leave and return are called. So I'll show that shortly in GDB. And it's 64 bits or 8 bytes long on 64-bit machines. And it's only inserted in functions where there's a potential of an overflow happening. Since a compiler doesn't actually know, it'll be more generous, but if a function, for example, doesn't read user input, you just won't see them. And the first byte will be null, just worth noting, because we'll have to deal with that. And that makes leaks a little bit more difficult, but it also makes it slightly more predictable. So we'll see that in GDB with our first example. This example is example 5. It's in the same repo as last time, so you might just be able to pull it if you already have it cloned. So we can see the code. It's relatively simple. There's a loop that reads input. This is actually the exact same read input function that we had last time. Yay. Thank you.
Perfect. Much easier to read.
So we can here see that this just reads without appending a null byte, which we used last time for our partial overwrite. It's the exact same read input function. And down here, we read into our buffer, and this is an overflow, and then it will print our buffer. And it'll keep doing this until exit is called. So this seems like straightforward. We exploited something very similar to this last time. But if we run checksec on it, we can see that it actually has full protection, which we haven't had any of these examples yet, but we'll be able to see that can still exploit these. So it will, here's the stack canary is found. That's what we're looking for here. So we'll look at this in GDB. So if we disassemble main, we can see this, when you see like this fs:0x28 type thing, this is where the stack canary is being set up. So this grabs a random value. It's actually each program, there's only one stack canary through the entire program. So this will grab the value, and it will be loaded into RX and stored in memory at RBP minus 0x8, which is right after we push the stack pointer and the function was originally called, so the return address. So it'll be right before those in memory. And then we can see at the end of main, right here, we're grabbing RBP minus 0x8, which is the same variable, okay, the stack address of it, and moved into RCX, and we check it against this fs:0x28 register with the expected stack canary, and if it's correct, we just jump down here, and if it's incorrect, we call stack check fail. So we can see that, let's just run this for example, example 5. We'll send a large input. I think the size was 32 or something like that of the buffer, so send a lot of A's. And then, if you remember, this was a loop, so we actually have to call exit. And you can see the no null byte is appended, just as a side note, because we can see the rest of our input here. But we get stack smashing detected. And I'll just follow the control flow in GDB, see if we can see this. Copy this. So we're gonna finish. Read our input. Bye. So if we step through these instructions, we print our input. Oh, we need to send an exit. I'm just gonna break right here at the end of main so that we can jump here quickly, right before it's stack break. At the address, right where we could see it's being checked. Continue, exit. So we could see here RBP minus 0x8. If we look in memory, it's probably a bunch of A's because we just put a bunch of A's in. Yep, these are 41 is hex for A, capital A. So we can step through this. Then when we make this comparison, the stack check fails. And it'll sig abort. I'll show this again and show you exactly what the stack canary looks like as well. So here it is. So it's at RBP minus 8. So we actually have to set it up first. Next. All right. RBP minus 8. That doesn't seem right. RBP minus. Oh, we need to look at the memory at RBP minus 8. So yeah, I gotta be careful versus print or examine with GDB. Okay, this is correct. So we could see it corresponds with up here, RBP minus 8.
Just for the audience, do you mind quickly re-explaining the difference between that print and that X and Y? One gave you the thing
Yeah,
you wanted and one didn't.
I will. Yeah, print just prints the value. So if we print a register, for example, BP, we can see that this is the same address. It'll be up here, RBP. Examine actually examines the memory edit, so it actually does the exact same thing as print dereference RBP minus OX8. We'll need to cast this too. Cast it to something. But yeah, you could see that examine makes it a lot easier, so I didn't have to type all of that out to dereference it and print it as the right size. So examine, you can specify types and sizes. So XG is hexadecimal giant, so 8 bytes long. So we'll print the whole thing. And RBP minus 8 is the address we wanted to read. Is this. And so you can see that it starts with a, it's at the end here because it's encoded with Little Endian, but it starts with zeros and then 8F, 2591, and so forth. And that's our stack canary. And if that changes, we can actually, I'm not going to bother setting it right now, but if I were to set it in GDB to just something slightly different, it would error. But if it's not changes, program ends normally. So this is example 5. Continuing on from 4 last time. You can see as we showed, checksec shows that all protections are enabled, in particular stack canary and pi are enabled, so we can't directly jump to an address without getting a leak first, and the stack canary prevents us from a simple overflow. So this example, we're going to use a ret to libc attack, because if you look at when we run it, example 5, it actually prints an address, and I did this so that we could not have to deal with a separate exploit to get a leak, just to make it more simple to demonstrate this example. But we can see here that this prints the address of set vbuff for us. But so we're going to be using a ret to libc attack, which we didn't exactly do previously. We jumped to an address in libc by overwriting the got to, we wrote like free with system. But the way ret to libc works, it's like the win2 example from Monday, but we're calling system. So we need a pointer to bin sh. We need to set up arguments, so like a pop RDI, and then we can call the address of system. So if we remember from last time again, we can calculate offsets. Once we have one leak in libc, we can calculate any other address in libc. So I'm going to start by doing that with this example. We can see it's printing set vbuff's address. Get a solve script started. Using pwn tools again, we can create a process. Example 5. And binary equals elf. Example 5. And if we remember, we were leaking the libc, so we can actually just get our libc to be easy to interact with. Libc equals elf. And the address of that is this. We can find that with LDD on the program. Example 5. This is the address of libc, or the path to libc. So now we can receive a line. This is where it printed the address of set vbuff. So and we need to convert this to an integer somehow so we can do math on it. There's an OX in front of it, so we're going to use Python to ignore that, and we're also going to convert it to int. It's in hexadecimal, so 16. Set vbuff header. I skipped the last two characters, not the first two characters. Okay, so this is the address. As a decimal, it'll be easier to read if we print it as hex. Yeah, you can see here. And we can also use GDB again to ensure that that is actually correct. So GDB dot attach process, and we again need to set context. Again, I'm using tmux here just because I want to be able to copy and paste more easily. But if you were in the VNC session, it's possible it would just spin up a shell without any further issues. If not, this is just the command that is called to create a new shell by tools. So it calls like tmux split and then GDB. And that's what is being called, but we need to be in tmux for this to work. And we can run it. And we can see our set vbuff adder is this. We can check to see if that's right. Set vbuff, and if we were to check, it is in fact correct. Oh, that's the next example. Not the next. That's the last example. So now that we have this address, we can start calculating what the other address is. So we see here, we can just copy libc base, and then from libc base, we can calculate whatever else. Libc base is set vbuff address minus libc.symbols set vbuff. And that's how we have our libc leak. So the next step in this example is to figure out how to break it. We talked about stack canaries. Just remember, starts with a null. We want to leak it in this case. So how do we, there's different ways to bypass it. I'll actually talk about this after doing the demo. Right now, we're just going to leak it. So we're going to use our non-null terminated string, right all the way up to the end of it, and print it. So we can look at, in GDB, run, oh, 7, 8. If we send like, our buffer size was 32. So if we send, I don't remember how many A's that is, some number of A's. Some number of A's. We can see that this actually overwrote one too many, but you see here, we can calculate the address. So at RBP minus 8, we start reading in RSP, I think. And we end in RBP minus 8. So minus RBP minus 8. We can do some math here. This is actually backwards. It should be because the stack goes the other way. Minus RSP. So it's 0x28. We can actually print this as a decimal so that I can understand it more easily. So 40. So we need to print 40 characters and then one more to overwrite the null byte. So 41 characters. And then we should be able to, it should just print our stack canary. So p.sendLine a times 41, and then we can do p.interactive. We can continue, and we see this gross data here. So 1, 1F, D. This should be our stack canary. Finish this. A. Stack canary ends with 4, 1 because we overwrote the null byte, so it should be 0, but then 3, 1, 1F. 3, 1 is actually a 1 in ASCII, so that prints as a 1. Then 1F, D0, 1F. There's something in there between them. There's the 6B, but that probably prints as something that's not be able to read. And then R is what, 7.2, A7, E9. So we need, and then it keeps printing some more data after that E9, which continues to go on until this null byte is found right here. Okay. So now we need to use Python to just extract this from the input. So we can count bytes here. There are this many bytes from the end and this many bytes from the beginning. That is, we can actually just count from the end. So this is like 14, and I actually have the numbers here, so it's just counting. Receive the line, and then minus 14 to minus 7. And that should give us everything except for the null byte, because we overwrote that, we have to add it ourselves, plus null byte, and it'll be at the beginning, because that's the order it is in memory. But if you were to print it as a little endian number, it looks like it's at the end. So this should be the stack canary, so we'll print hex unpack 32 or 64. Create pwn tools tool to unpack it with little endian. Leak. Print. And hopefully that's correct. If we align parentheses. Continue. Okay. So this is what we're getting here. And if we go back to main, we can ensure that this lines up. This db df. So that is the same. So now that we have the stack canary, we should just be able to cause a segmentation fault rather than a stack canary error. If we send 40 A's, our stack canary, and then something, and then call exit. So let's test that out. Payload equals payload plus equals A times 40. Leak. It's already encoded correctly because it's not, it's just bytes. And then we can send like A times 8 or something. We'll actually use B, so it's different. So if we continue, we need to type exit, and we still get stack smashing detected. Let's see what's going on. It's because there's so A times 40, it's our leak. there might have been a, let's just run it again. See what happens. You know what we didn't do? We didn't send our payload. And then we could also send the exit while we're at it. Remember to send your payloads, guys. I've actually spent a long time debugging things where I didn't send the payload in the past, so be aware. So we can see here, this is a SIGSEV. That's a segmentation fault. That's not a static canary error. We got to the ret instruction. We see that we're trying to return to B's, 42424. And RBP was set to the C's because it checked that first, then it popped the C's into RBP, and now it's trying to jump the B's. So now that we are able to control the return pointer, it's just a matter of getting it to call system with the desired argument. The only address we have, though, is libc addresses. So we can calculate the address of system. System should be easy to find. System, we can do this the same way. Libc base plus libc.symbols system. But now we also need to set up the argument. And we don't have the address of the binary in memory because pi is enabled. Check sec. Position independent execution. So we could actually use the exact same approach that we used to leak the stack canary by like writing all the way up to it. This address here, actually. So we actually did end up leaking it already. If you saw that the 0 was here, binary address is here. And then once we have that address, we can use it to ROP. But I'm not going to do that. We have libc already, so we can check libc and see if libc has any gadgets that we can use to ROP with to pop something into RDI. We're just looking for a pop RDI in libc. So we can find what libc is. ROP gadget, remember that's the tool that we like to use to find gadgets. Pop RDI, pass binary. And libc is big, so it's going to take a little bit of time to calculate and grep. There's a lot of pop RDIs. We just want a pop RDI ret, so I could have grepped for that directly, but it's here. And these are offsets in libc, so we'll need to add this to libc base. We should be able to calculate that fairly easily with the same approach that we took last time. But, oops. What I'm going to do is use pwn tools to find our get. So we can do libc equals ROP, which is libc ROP equals ROP, which is awesome. So now we can just find pop RDI equals libc base plus libc ROP dot find gadget pop RDI ret. So this will just search libc for our gadget, and I could have copied that address from before. It'll probably end up with the exact same gadget. There might also just be multiple in libc, but pop RDI. And then we can grab the address of a libc, or of bin.sh, sorry. libc.search bin.sh. This needs to be a bytes. And we need to put a next around it because it's an iterator in Python. And we want to grab the first element in it. This actually we need to index and grab the first element in it as well. No, we don't. Find gadget will automatically. But we do need to grab its address because it returns a gadget object. If you look at the PwnTools docs, there'll be more details about that. But like you can find details about like its argument, other useful metadata about the gadget. And this is NSH. And so this should be good in theory. You'll see soon that we have a similar issue to last time. Thanks for putting those docs in the chat. You can see that we have our leak, then payload equals pop RDI. We need to pack this 64 for a 64-bit architecture. It's actually wrong. It'll be down here because that's where RBP is. So 8. Okay. So this is where it starts. Pop RDI, then bin sh, and then system. Then we'll send the payload. Then we'll send exit, and this should work, right? But when I was trying this, it didn't end up working. See, if we continue and run, we still get a 6F. And this is actually for the exact same reason that the other challenge didn't work. Last time we had to just drop in a random ret. So just ret to fix our offsets. I think this is an issue with Ubuntu 18.04 in particular. Because on other machines that I've worked on, I haven't run into this exact same issue. So I don't know exactly why, beyond like the instruction requires alignment. But we'll throw in a ret. We'll continue. We see that it's just trying to continue, and we have a shell. Because it did call system. I'm going to actually step through that in GDB so that we can see it. Finish, finish, finish. So if we step through main, we're calling puts, then we have to read our payload again. And we'll do this until we get exit as our input right here. And we can keep stepping through. Exits our input printed. And then we check for exit. And it is exit this time. So we get ready to return. We check the stack protector. And we could see right here, it was set correctly, even though our input continues after it. And then step through. Step, we make it to leave, which will pop these A's into RBP. Then we get to ret, which is now going to return to this address, which goes to pop RDI. You can see here, we'll step instruction. Pop RDI, what comes after RDI? The pointer to bin sh that we just searched for. We can step, turn, see bin sh is up here in RDI. And this is our random extra ret that we had to throw in to fix alignment for system. And we're in system, we can continue, and we have a So that is how to leak a stack canary in at least one case. There's a bunch of different ways to leak stack canaries and bypass them. So sometimes you'll see format strings, which we'll just talk about on this slide. And then you could just tell the program to print like 1,000 bytes or something. If you like tell it what the length of your input is, then it tries to read that many, even though your input's not that long. Or something along those lines. That'll also allow you to leak the stack canary. You can out of bounds index if you're trying to read like the 10,000th item in an array that's only 999 items long, and then you can find the stack canary that way. Or like we did, non-null terminated string that we can continue reading afterwards. Some other approaches to bypass the stack canary: brute force. So if the program restarts or forks or has a try catch that can catch a seg fault, some programs do, which is dangerous, by the way. This will allow you to brute force one byte of the stack canary at a time. So like you can loop as many times as you want until it doesn't crash with a segment or with a error of stack canaries, with a stack canary error. And if you get one byte, then you can do it again with the next byte and so forth until you brute force the entire stack canary. Or you could just ignore stack canaries by using something that allows you to write to an offset. So if you have an out of bounds array index, you probably don't really need to leak it, the stack canary, because you can just write past it. Same with format strings, but it depends on the protections on printf. And you can just write somewhere else that's not after the return pointer as well. I have the hiccups now, lovely. But here's format string. So this is our second example today, sixth example this week. What's wrong with this code? Anyone see it? It's this line here, printf input. Printf, the first argument to printf should never be user input. You can see here what the printf format or printf function declaration looks like this. So it's a format string and then variable argument. These are called variadic arguments, where the number of arguments is unknown at compile time. And there's no, in C, there's no consistent way that's used to pass how many arguments going into printf, because it's different each time you call it, and you just don't know. So printf has to figure it out on its own. And the way it does that is it looks at the format string it's given. So like %d, it assumes that it gets another argument. So there'll be a second argument that it can read from. And you've probably seen printf format strings before. There's stuff like HHD. This will be a half of a decimal, so this will be a single byte. You can use like a $sign to print the nth argument. This will print technically the fourth argument because it'll be the third argument after the format string. And you can dereference something as a string. You can print it as hexadecimal. You can throw in some padding and print something as a character. And the %n, that's a very fun format string specifier. What it does is it writes to memory. So if you have a variable count or something, some pointer to a variable, then if you have %n, it'll write the number of characters printed so far to that variable. So in this example, you print 4 A's, and then it will write 4 to n, whatever is in n, to the 12th argument, 13th argument. And that's super useful if the user controls this format, because we can write to memory now. In the most modern protections, there's what's it called? Fortify source. You'll see if we go to this example 6. See, it's compiled with Fortify source 0. Fortify source fixes some security issues with some functions that may involve breaking changes in some cases. In our case, that's %n. So it disables %n if the source is fortified, which is somewhat common. in modern architectures, it's very common because I had to actually add that flag to the compilation to disable it. But we'll see %n being used. But format strings are great for leaking things, even if %n is unavailable. So if you remember our calling convention, this will be still the same for variadic functions. So we can access values in RDI, RSI, RX, RCX, R8, R9, and then the stack. So if our input is on the stack, what do we think that means? That means we have a significant advantage when we're attackers because we control both the format string and the argument because the arguments are on the stack. I'm going to show that right here actually. So we're going to look at the code, example 6.c. So we're actually first going to look at we're going to look at the very beginning first. So print input to this random. So a random number is generated, put into this stack variable, and then we read input right here into our input of size 512 bytes, and then it prints our input just like you saw on the first printf slide. So right here, input printf, no arguments, GDB. But if we have like percent, just show %a, it prints something. We can mess with it. And since let's see, we do like %p. %p is a good one because it prints it as a pointer based on the system that you're on. So it'll be a 8-byte pointer in our case. If you're on a 32-bit system, it'll be 4 bytes. Otherwise, you might need to do like %lx for a long instead of just the size of a regular integer. And it'll also like throw ox in front of it. And I like using dots when messing with format strings, trying to figure out what's going on, because it helps me separate memory that I'm leaking. So see, this is just memory on the system. The arguments. This is probably the value in the second argument to the function, because format string, and then next argument that we're looking at. So this will be RSI. And if we were to run this in GDB, debugging symbols are compiled here so that we can step through it easily. So we can use next instead of next I. So we'll read our input. It is, we'll just have %p dot %p. Throw in some number of those. And then we'll step next. So this is our input printed. Should be, if I can scroll, can't scroll. Um, sure. We'll just shrink our screen a little bit. Let me know if you can run.
Still seems
Yeah.
readable to me.
Input p. That's unfortunate. I know. We can disable the All right. Next. So what is her name? Send %ps. Next, and then this is our input printed. So if our hypothesis of RSI here is correct, we can print RSI and it should be that value. And it is in fact the same value. And then we were trying to figure out what the stack var is. So we want to leak stack var somehow because it's on the stack. Our input is also on the stack and the arguments are on the stack. So we want to just figure out which argument to the function is stack var. The easy way to do that, we can print stack var. We can look up here. We see right here, this looks like our input, stack var. So if we were to continue, let's print this as decimal. This is the value that we leaked. So we'll continue, send that input, expecting it, and we can make it through. Let's see if. Yeah, so it didn't print sorry and exit. It would have print sorry and exit if we didn't input that stack var as expected. So what is a more direct way of doing that? So we can see which argument this is. 1, 2, 3, 4, 5, 6, 7. The 7th argument. So we can run example 6. And we can $7. So this tells it 7th argument. We're going to print this as a long hexadecimal number because we need the whole thing. Because if we were to print this as just hex, it would end up printing this value, the lower values, the least significant bytes. And each argument will be another 8 bytes. So we just totally miss this in memory unless we print the whole thing. So be careful to use %p usually when just trying to dump all the memory in printf. So we'll say this is our name because it definitely is. Small. We'll get the actual value. I'm just using Python here. P is an alias to Python. So we can send the integer and we are able to continue execution. So I'm going to convert this to a solve script so that we can save our progress. Which example number? 7. P dot send line. This is actually probably example 6. Send line, what did it say? Percent $7 to get the 7th argument. Leak, receive line. And then there's a hello in there, so we'll grab the split. Let's see. We're gonna actually receive until hello base. And so then this should be the start of our input. There's an OX in front of it if we have this %p here, so we'll need to skip that. Or we could actually use LX to avoid the %p, so we don't need to get that. And then we'll just read until the 8th character in it because we want 4 bytes and that will be 8 characters. And we can print, we'll actually convert the print hex leak stack var, and we need to actually convert this integer 16 because it's hexadecimal again, and then we can send line leak and p.interact. to ensure that we are correct. Int can't be converted without a. This is an explicit base. Oh, because it's not. We need to grab colon it. Yep. So here's your stack var, and we're able to continue execution. Sample. Let's see. So now we can start looking at the next step of this program. You can see we have comments here which kind of help guide us along. So this one, we're supposed to leak an arbitrary address somehow. This means an address that we choose, not just something that's already on the stack. Then we can write to that arbitrary address somehow. So how do we get to choose the address? Remember, as we talked about, additional arguments are passed on the stack. And our input is on the stack. So we can find where our input is stack with like 3. We just have a bunch of A's. And then we can do the %p thing again. We can also, you should also be able to just calculate this if you know where in memory it is. But I find the lazy approach tends to work just fine. So if we look here, where's our, we find 41414141, which is in fact A. So we can figure out which argument this is. 1, 2, 3, 5, 6, 7, 8. Our input starts as the 8th argument, and you see here these are this pattern, 2020. These are spaces, and then 2e 725, 2e 7025, 2e, so forth. That's the rest of our input. %p dot, p dot, %p dot, so forth. The 20s are the spaces. So we can use our input as an argument. This was the 8th, I believe. Yeah. It's the 8th. We start at the 8th. So we can look at the solve script now and try to leak that next part. Or leak, just see if we can get the next step starting to work. So we'll set the payload %. We said we were the 8 $sign. We'll just continue to use P for now to leak, but remember that %s, it will dereference the argument and print it as a string. So we can just print bytes in memory if we have an address. And the other thing we need to be careful of is, so if we can do this, like, so we send our A's, and the start of our input is %p, line, payload. So this would work, but the problem here is if the address we were trying to leak has any null bytes, printf stops at null bytes. So fgets will read null bytes for us as much as we want. But printf will only print until you get null bytes, and it won't continue printing any of our format strings and won't be very helpful. So we need to change the order of this up. We need to put this here, then we need to put our address. But this won't work because the offsets are different. So we need to bump this up to 9, and then ensure this is 8 bytes aligned. So this should be 1, 2, 3, 4, 6, 7. So we need one more byte here. And then our A's should be here. And we can check and see if it's correct if this prints A's. And we see that in fact it does. And now we can use this payload to print an address. So if we change this to %s, we're going to segfault because we're trying to reach the address. Yeah, see, 6F. We're trying to print the value at that address. But we can do something like leak a libc address. last example gave us our libc, but this time, if we want to read an arbitrary address in the global offset table, if you remember last week, Monday, we talked about leaking and using the global offset table to read and write. If you have arbitrary write, you can modify something in global offset table and leak values in the global offset. So this will be set viba got so this percent, we can first use %p to just infer that everything's correct, which is not. We need an equal here. We also need to be able to grab symbols from the binary. We need canary equals health 6. And we need this bytes. And it prints garbage as we want. And you notice that it doesn't print anything after. That's because it prints until it gets a null byte. And the null byte is actually, the reason we're getting this, because we're using %p, it should still work, just phone tools is overlapping. But if we use %s, this, in both cases, it stops printing because setVBuffGot has a null byte in it. But there's a little bit more confusion going on because phone tools inserting something. You see, it's interesting we got a sorry here. I think there's probably a new line or null byte. But that worked. And something's being leaked, but it's hard to see. So we're going to just try to receive it. We can receive until we get our 4 spaces, which kind of nice that we have spaces here to just reference by. And then we're going to receive 8. We're actually just going to, because this should print and then start reading input. So the whole thing should be the leak that we want. It might not be correct length because it won't print null bytes. So we can do oh, wait. I was wrong about that because if we look here, it's printing the value as that bbuff got at the beginning. So it's right before these 4 spaces. So we can just grab leak equals up to the last 4 bytes. And then we need to receive just the new lines afterwards. So I'll grab that with p.receive. And then we can print, or what is it, set vbuff equals leak. But leak is won't be exactly 8 bytes long because null bytes at the beginning of it. So we can justify it. We want it to be 8 bytes long. We're going to left justify it with null bytes. And then we can unpack 64. This print set vba pack set. We have a partial address, which is not exactly what we want. I'm going to check this in GDB to make sure that everything is correct. So we're stepping through. Print the address of set BB buff. We are getting 63B69. We need to grab the last 8, the last 4 bytes. And we can try to continue. And we see that we do have set vbuff, but we don't actually want the last 4 bytes because there's 2 spaces in here. So we're gonna take the last 6. If we print set vbuff, hopefully this is the same address. Yes, it is. So I can step through this in GDB, walk it through, get back to main. So this is our first input that we print, and we use it to leak the stack variable. So our input is lovely, but this is the 7th argument, and printed as a hexadecimal long. We use Python to extract the value from there. This is the random number that's generated. And we can step through, we compare, and it is in fact the same, so that compare succeeds. Then we read input again. If we look at our input this time, we're gonna print this. Sizes mean. All right. So this is our input. So these are the this. Yep. Input. Okay. So this is 9s, and then after that, after the spaces, we have our got address of set vbuff, which is easier to see like this. 60D E8. G. So that should be correct. Yep. And then we can continue, and we have one more chance. This time we can use it to write to a location in memory. Writing is sometimes a pain in printf. If you think about how %n works, it writes the number of characters written to memory, which that means you have to write as many characters as you want to write to memory. So not easy unless you're writing very small values. However, you can use arguments like %HHN, .gdb, %HHN. This will write a single byte to memory, and because it'll overflow if you write another 256 characters, you can have it write a single byte, and then you can do that multiple times in a single input. So I'm not going to actually walk you through the entire process of how to do that. Pwn Tools has a useful function. It's format stir. Pwn Tools has a format string library. I might be able to new window. You can see Pwn Tools format string. Lots of useful, like format str payload. It will automatically calculate a payload with a certain number of writes to certain locations. I've had some issues with it and some awesome successes with it, so your mileage may vary, but I've already written up a solution to this one that will automatically generate, will generate a payload that we need based on based on this specific challenge. So we can copied it in here. What it does is it will calculate, it'll get padding correct, and it will calculate the, length of payload. There we go. We'll get the address of a one gadget in this case. I'll get into that quickly. And then it will calculate, this is a single byte that will be written to memory. So it prints this many characters. %C, I'm going to talk about that real quick. Example 6, %10C. So this prints something as a character. But if you see here, this is setting. There's 10 spaces here. C is great for padding. So if you have %10C, %100C, %1,000,000C, whatever, I think this will also work with like %D, %42. It was looking for an input of a number. Yeah, see, prints an argument as decimal with some amount of padding. And this is a way to, in a short number of characters, write a lot of characters. And so we can use this to, for our payload with %ns to get the correct values written to the correct spots. So I'm going to start calculating addresses now. Libc base equals set vbuff address minus libc dot symbol set vbuff, and we also need to grab libc. So c equals all right. So libc symbol set vbuff, and we can calculate from libc base. Can get. We're actually going to use a one gadget in this example. So one gadget is just, you can return to a function and it'll directly call libc. I'm gonna one gadget. So one gadget will, I think it uses like some weird form of, some simple form of symbolic execution to find gadget. So if you have like certain arguments, R10, R12 in this case, set to null or the value at, then you can call exec v bin sh and it will just work. In our case, we have a different libc. The address of libc is a so we're going to put this in Ubuntu libc. This is on my machine, not in the Dockers, because I have one gadget installed here. Sorry that we couldn't have it installed in Dockers. It will be the same on every system though. Every Docker will be running with the same libc. So your offsets will be the exact same as mine. And you see that this Ubuntu's Dockers is actually better than on my actual system's libc in terms of constraints because there's fewer of them. So this one's RCX has to equal null. There's a couple others, but it really depends on the system, which one, or the challenge, which ones will work. Oftentimes you can just try multiple of them and see what works, what doesn't. For this challenge, I know that this one will work, so I'll just use it. So one set equals this address right here. So we can grab one gadget address equals base plus gadget offset. So this is the exact same thing as finding some symbol of printf or something in libc and adding it to libc base, but we just know that our one gadget is in there. What we did with the ROP, we're using libc last time, but using a one gadget. Or not, won't always work for you, but when they do, it's really nice. Let's see. So this generator, this payload generator, generates the addresses of the one gadget. So it gets one gadget address and writes that many characters, then writes to the certain index. This will be starting at this is actually generating a format string. I did this when I was writing byte that it wants to write to, and then we'll figure out what the start index of our input is, because we started at index 8. Remember up here, so this was 9 because we had one more after. 8, divide the size of the payload by 8 to calculate where we're actually starting after our payload. And then we can build up the format string by using Python's format to replace this in each of the instances of this with the address that or with the value that we need to write, with the index that we need to write to, I'm sorry. And then we append the addresses that we want to write to the end of that, and they should be at the correct index. And then we can send the full payload. I'm not going to spend too long debugging this if it doesn't work for some reason. Python 3. Yeah, so this did end up working, but when I was writing this challenge, I had written out that entire logic for generating the payload. I'm going to print this payload actually so we can see it. So the reason that didn't work that time is probably because of new line inside the address of set vbuff. So it's not going to work every time because of that, just so you know. And here we are. You can see this is our full payload. You could build this by hand. I think it'll be the same every time, but it was easier to just write the short Python parsing to do it for me. But so it'll print 92 Cs. It wants to write 92 to the first address because that was the bytes in our in the address of what was it of the one gadget, and then writing to the 21st argument 1 byte. 21st argument is all the way over here. Something like this right here, or something along those lines. And so that's the address that it's writing to. It writes to it, and then add 164 to 92 to get the number of bytes written already to be the correct value, and then you can do it again, and just keep doing the same thing over and over again until we write a bunch of individual bytes to memory and change the address of exit. I'm going to just step through it in GDB just one last time, and then we'll move on to quick overview of Heap. So if we get to main here, we can step through this. So we got our leak at the beginning. Here's our input that we read, we print it, and now we can check set exit. Exit's the one that we overwrote. Since we don't have an exited got symbol, I'm going to print to instruction. To instructions at exit PLT. And so this is the address that it's reading from. So this is exit at got. So /xg to examine memory at it. And so this is the value that we want to call. So this is our one gadget. So x/I at that address. So we can see here exactly what it does. So it calls execbe with some arguments set up. So one of these should be bin sh. So this should be a pointer to bin sh for us. And then we had to have RSP plus 70 set to the correct value so that RSI would be 0. And with RSI 0, we were able to call execve gives us. All right, so that's that. Any questions on that? On format strings in general? I'm not going to explain with too much detail how %n is used to exploit. It's slowly being phased out, and basically to figure it out just takes a bit of experiments and tinkering with. All right, that was example 6. And now I'm going to talk briefly about heap exploitation with hopefully a relatively quick demo as well. So heap exploitation is our most common vulnerability class in modern software. In like the big stuff especially. So like iOS, OS operating systems, or Chrome browsers, or even just other software because of modern protections in part. And standard buffer overflows are getting easier to detect and avoid. So use after free is actually the most. I think it's #1 now as of a couple of years ago probably. It used to be buffer overflows. So there's common heap vulnerabilities or heap overflows. So if you allocate something in the heap with a call to malloc, and you write too many bytes to it, it will cause some data corruption, and that can be exploited somehow. Use that for free, so you free something with the function called free that you had allocated with malloc, but then that object can still be used somewhere else. And so that's a very exploitable. And then double freeze. So if you free something and then you free that same thing again, then when you allocate memory, it will allow you to allocate like 2 overlapping chunks or cause other similar issues. And a wild free. So if you call free on a pointer that was never allocated with malloc, and that can also cause issues. A lot of issues with heap. I'll give you an overview of what heap is, how heap works. So the 2 functions that are most commonly used to just represent heap, malloc and free, all interactions with the heap on Linux essentially boil down to a malloc or a free. There's other functions like calloc or realloc array or some stuff like that, but ultimately they just allocate memory via a call to malloc essentially. And free will free memory. So if you allocate memory with malloc, it grabs it from the operating system or somewhere, and then free will either return it to the operating system or it will put it in a free list. Free lists contain all your freed memory so that malloc next time can be faster and not have to grab memory from the operating system, but can just grab a chunk that you're no longer using, and it just allows for much more efficient memory management. And there are many different heap implementations, and the only one I'm going to be worried about right now is ptmalloc in Linux glibc. So this is what you see in modern Linux operating systems. Windows uses a different version of malloc, different implementation, and other operating systems, or even versions of Linux, might use different malloc versions. As I mentioned a little bit, free add something to a list of memory allocations. That's a linked list, usually a doubly linked list. But the way it works is free something, adds it to the list. There's many different lists actually, depending on size or how many things have been freed. Different versions of the glibc will have different types of lists, so it can get somewhat chaotic. And there are a bunch of security checks usually when like freeing or allocating to try to avoid double freeze, wild freeze, use after freeze. So for example, double freeze, it'll check against like the next element in the list to see if it's the same one. If so, it knows it's a double free. There's a check somewhere along those lines. Checks with the size, so if the size is way too big, something's corrupted, it might cause an issue, and it will intentionally crash the program if that happens to prevent exploitation. And Heap understanding. So I'm not going to be able to go in a lot of detail, unfortunately. Source code of libc, absolutely fantastic. You can see here, there's super detailed comments explaining exactly how everything works. A chunk in memory looks like this. There's the size of the previous chunk, size of the chunk in bytes, and then this is where the chunk, your memory starts. Put your data here, and then the next chunk starts. Some overlap in memory, which is kind of convenient because the next chunk has its size right here, but that's the next chunk size for you. So there's some overlap with that, which causes some issues when trying to exploit Heap, but also sometimes enables exploits if you can overflow from your memory into the next chunk size, for example, or even into the next data. And then when a chunk is freed, you can see here that it changes from your memory, from your data, to a forward pointer and a back pointer to the next chunk in the list. Forward pointer will point to whatever the next free chunk is. And so when you allocate a chunk, these pointers will be deleted. You can put memory here. And the next element in the list will then become the first one. And back pointer the previous one for different types of lists. And if you're in CS here at Purdue, we get to implement malloc, which is awesome to help you understand exactly how it works. It's not PT malloc, it's not the exact same, but it gives you a great understanding of the concepts behind malloc, what might be exploitable or not, if you're thinking about that when you're working. So I have a quick Heap example to wrap up this day with. So in Ubuntu 18.04, we have Tcache. Tcache is basically one set of lists. Let's see if I can find it in this code. Use Tcache. So this is what a Tcache. This is what. Yeah, sure. But there's multiple Tcache bins. Some max size. Tcache is used for small sizes. So like 32 bytes will be in there, maybe even a couple hundred depending on machine you're on. But small chunk sizes. And it's meant to be fast, quick, and it's new. So it has fewer security checks, which is why we're going to be using it. And so by default, when you free on Ubuntu 18.04, when you free a small allocation, we're going to be using 32 bytes in this example. then it will be added to the T cache. And let's just look at this in memory. GDB with Jeff has a heap command. So here's the code actually. 7 does. So we allocate A, we allocate B, we free B, we read into A, we allocate B again, we allocate C, we read into C, we free A, we free B. So we're going to be exploiting this to get a shell, but I'm going to first walk through what this looks like in GDB. 7, break main, run. So if we step until our first allocation, so we can print A, this is a heap address right here. Some value in the heap. Heap chunks is a nice command that we have in Jeff. So there's some chunks already allocated. We have this top chunk, and this chunk that was allocated near the start of the program probably, just by libc somewhere. And this is our chunk. We know it's ours because it has a small size. The other ones have like a large. Small size, our chunk. And we can see, we also know it's ours because it has the same address. But then we could step again. Next, now we free B, so heap chunks. We allocated B first. So we see we have 2 chunks now. So this is B, this is A. And we also freed B, so we could do heap bin. This shows us all of our heap bin. T cache, we like. That's what we're looking at now. So there's different indexes with different sizes. This is the T cache with index 1, which, because it has index 1, it has a size of OX30. Different indexes are different sizes. All that means. I think there's probably 7 or 8 of them. Same idea as fast bins, just T cache. And T cache, if I didn't mention yet, is a singly linked list. This makes exploitation easier, makes adding checks harder, and is just generally easier to understand. So we see here, there's one item in the list, which is B, which we had just freed. So if we step next, we need to read something. Next, we can allocate. If we look at, now that we just allocated something, heap bins, we see that there's nothing in the T cache anymore. Cache is empty. That's because malloc, when we used it, had looked in the T cache first to see if it could find any address to leak, or not address to leak, any memory to allocate. And it allocated it, and so it's no longer in the T cache. So we can read into C with something. Then we could free A and then free B. And if we look at heap bins again, we see there are now 2 chunks because we freed 2 chunks. So here, and it points to this chunk. I'm going to use this heap chunk command to give us more details. Heap chunk. And we see here that chunk address is this, has some flags, has some size. If we print this, x/4fg, we see that this is in memory. This is the address of the chunk. This is in memory. What? Go to this line. Okay. This is the address that we're printing right here. And this is a freed one, so we're looking at the right one. And so it should be a forward pointer in the next chunk, and the back pointer does not exist with the T cache because it is a singly linked list. You only need forward pointer. So we see here, forward pointer, and that in fact is pointing to this next chunk in the list. This is this address, this address. We can follow that same idea, print this guy, and it's 0 because it's the end of it. And now that we have this, we have an idea of what we might be able to do to exploit it. If we can change this forward pointer, or maybe this one, either of these forward pointers, when you allocate a chunk, you can control which address is being allocated. So if there's a free chunk that comes after a chunk that you're able to write to, you overflow into this next forward pointer, then we can we can allocate, then malloc will return an address that we control. So the idea in this challenge is A is allocated, then B is allocated, then B is freed. So this is the situation I was talking about where you can write A and you will overflow into the free version of B. So we write 128 bytes into B, which is enough to overflow. With our overflow, we can, With our overflow, we can control the value that will be allocated. Not here with B, because this allocates B that was just freed. But then the next pointer in B is what we overwrote. So this is where the next pointer in B was pointing to. So we can control the address of C, and then we read into C. So a solve script for this is actually super short and simple, but conceptually understanding exactly where everything is in memory, and as Heap gets more complicated with like partial overwrites or messing with sizes of chunks, stuff like that, it can get messy. All.py. And I'm gonna just go through this somewhat quickly for you. We need to set context in terminal and process example 7, binary in libc. So first thing we needed to do was get the, so if we look at the code, it'll actually, when we run it, it prints the address of libc value for us. This is to just break ASLR and make exploitation simpler. This is the address of set vbuff again, just like the demo today. So we can grab this, integer, set vbuff. This tends to be somewhat repetitive, but it's only a very few lines of code. I think tools needs to do it for us automatically. But here we are. Set vbuff adder. We can calculate the libc base. And then there's this free hook thing. Free hook, which I'm going to talk about briefly during this exploitation. It's a writable location in libc that is called every time free is called. It's a function pointer. Very convenient when exploiting heap, or even just code you have an arbitrary write, but you don't have you only have a leak of libc and you don't have a leak of like your code because pi is enabled or something like that. If you overwrite free hook, you can force a certain function to be called. This works best with one gadgets because you don't really have a good way of setting up arguments for it. So we're gonna do a one gadget here as well. I already grabbed the good offset for us. It's the same idea. It's actually one of the ones available. This was just, I think this is one where RSP plus OX40 has to be 0. Something like that. It might have been OX70, I don't really remember. but same idea, and then one gadget. Address equals gadget offset plus libc base. Alright, so then what we needed to do was first we overflow, and it was, we can check the size. GDB sample 7, run. Finish, finish. Okay. So if we allocate A and B, okay. Print A, print B. So we see that there's OX 30 bytes between them. And so we need to write 30 bytes and then OX 30 bytes, and then we can overflow. So A times OX 30 plus, this is the value that we want to write to, remember? So it will, write the address to, this will be the address that free will be pointing to, the next pointer will be pointing to in the free list, and then that'll be allocated with when malloc tries to allocate C. So I'm actually gonna just do this quickly for us so that, because it'll take very long otherwise. But so what, I'm subtracting A here because we need to send the size of the chunk. Do you remember the size of chunk in bytes right here? This is here. And one of the checks if size is way, way, way too big. So we give it a small chunk size. You give it the same size. The size was actually OX30 if you remember when we were looking at in GEF. So P64 OX30. And then this is the forward pointer that we want. So the forward pointer is the address of free hook. And then p.interactive. So this should, are we sending that? Yeah, we are, okay. All right, so we send the input and it tries to read one more input. We can read it and it segfaults. The reason it segfaults here is because we're trying to call free hook that we are overwriting. So, and we overwrote that with like ASDF. So gdb.attach process, and then p.set p64 one gadget. One gadget. So we can step through this in GDB. Next, next. So this is where we free A, so heap bins. So we see nothing is in, oh, I wanted to show this. This is after reading A. So we overflowed into this, and we see that this was our original chunk. And then we overflowed into its forward pointer. So if we look at G, this guy, this is exactly the same thing in memory we looked at before, but this is the address that we controlled. So this is the R1 gadget. So, or this is free hook, sorry, not one gadget. So free hook is writable location memory. So we will step to the next instruction, and we can print B. So this was just allocated. Heap bins, we see there's only one chunk now, and this is the address of free hook. So if we step to the next instruction, and then we print C, this is the address of free hook. Now we read into C. Next. and then we can print free hook. Instead of free hook was zeros before. Yeah. So this isn't the address. Yep, there we go. So this is free hook, and this is the value that we have just written to free hook, which is our one gadget. We need instructions to see exactly down here. Yep. So that is correct, and we should be able to step to the next instruction where it tries to call free, and it now executes our shell bin dash. Sweet. And so that's a quick heap example. Hopefully that gives you a good idea of like what a vulnerability might look in heap. There's a ton of different ways to do heap exploitation. So for example, if you were able to still write to B, like if this was F gets B instead of A, where B is free, it's the exact same idea. It's actually, I could probably make it work. So this is a double free actually it's probably not gonna work because of checks. But the idea is the same. So if you have a double free, it's just the offset's different. Instead of overflowing into it, you can just write directly into base that it thinks is okay to write to. But you can still change the forward pointer. So hopefully that gives you a good idea of how the heap works. But I'm open to any questions about the entire presentation or demos yesterday, today. But that about wraps it up. And I've on the last slide, you can see the slides on the GitHub. I believe it's linked in the chat. But some quick references if you want some heap resources. If no one has any questions, then thanks for watching. And right now, Boilers is hacking away on dark CTF. So feel
Dark
free to.
CTF, Nathan. That's really ironic, seeing as you are sitting in the dark.
I know, but it was light outside when I started.
No, it was funny. It was very hacker of you to just like retreat into the
Like
darkness over the course of your presentation.
my light's on too. It's just the fans not spinning. Okay, that's funny. Am I like actually super dark, or does my screen kind of light up my face?
I can see your lit up face with the screen. Like I was saying, it's very hacker of you.
Yes. Look at that light.
Wow,
Crazy.
good stuff. Questions? Questions? I'm gonna this is the last really like actual training one. Hardware is going to be more of a survey, and then pen testing is also going to be a bit more of a survey type of training session, but we'll have the README and the GitHub for our 2020 training will be updated with a lot of resources for more practice problems, places to look for more information, etc. Um, over the weekend. So look for that.
Yep, do that. All right. Thanks again for showing up, guys. Sign up for the CTF if you haven't yet. Next weekend, next Saturday.
I'll drop
Should
the
be fun.
link in chat, but we're about to log off, so it won't stay there too long.
It'll be there for everyone who watches on YouTube.
Perfect. Sweet.
Have a good one, guys.